Hey everyone, welcome back. This is part 3 of our linear regression example that we were working through within R. If you are just now joining us, you should check out the previous 2 videos and I'll post a link to those. So let's go ahead and dig it back in and get started. Alright, so where we left off, we had just estimated a baseline linear regression model, and we worked through the summary of that, everything that R produces for you and then prints within the summary command, and we talked about all of these different things and what they all mean. So, previously, at the beginning of the second video, I decided to add another library here, this R MISC library. We'll hopefully get to that by the end of this video. Alright, so now that we've actually gone through and seen all of the different output that R produces, we should probably at this point add a separate R chunk, and we should use this stargazer command that we previously loaded from the first video. Now this is the stargazer package. The idea behind this is to take summary objects for regression models like a linear model and produce a publication quality table. And it's really powerful. It's lightweight. It's got some really unique features to it. We don't need to go too heavy in this, but I am going to set this for HTML, which means I don't want to preview this code within the R Markdown environment here. We're actually going to want to knit it so that we can show that separately. Alright, so we're going to first use the stargazer function within that library, and we're going to put in our first model that we estimated. And what do we call that? Yeah, first underscore model. All right, so we'll put that in. And you can use other models as well. You can list multiple different linear regression models, but we're just going to use the one. We want to put type, and then we'll put HTML here. And because it won't necessarily limit this, we'll kind of limit the digits to 3 in this case, just for reporting standards. Now, if you go back up here into the line 71, where you've got after you've inserted the R chunk here, inside the curly brace, I'm going to put a comma, and then I want to put results equals, and then we'll hit as is. Now, the reason for this is the stargazer function will actually produces HTML code. And so if you don't do this, it's just going to print the HTML code within the document. And that's not quite what we want here. But we want to say, okay, print these results as is, so that it will take this HTML code, interpret the HTML code, and then insert it into our knitted document. If you're using LaTeX, you would put LaTeX here. If you're just doing say a Word document, you would say type equal text. So let's try this out, and we'll knit the whole document. Give it a moment. Sometime today. Come on. You can do it. You know you want to. Coffee break. There we are. Alright, so here we have everything that we had previously produced, and then we have our actual table here. We could center this if we wanted to, but in the meantime I'll just leave everything justified over to the left. Alright, so here what we see, I haven't changed like coefficient names or anything like that. You may want to if you're putting this into an actual reported paper or something like that, but in this is generally exactly how things are produced here. We have the dependent variable that we're trying to estimate listed. Of course, if you have different models, then you'll have different labels for your dependent variable. In this case, we just have the log of salary. We have all of our coefficient estimates. We have our standard errors reported in parentheses, which is pretty standard notation. So everything, you can kind of do a one-for-one comparison. We have estimates, we have standard errors. We don't print t-values and p-values within most standard reporting in, at least definitely not in the econometrics literature, but in most applied sciences we don't do that. But we do all these stars for significance. We do include those, and so we can easily, real quickly see at a glance whether this is a statistically significant effect or whether it's not. And so all of that is included here within the table. Of course, we have the number of observations included here, 397. We have both our R squared, our adjusted R squared, our residual standard error, all of this information that's printed down here below, as well as our S stat. and then kind of a little legend here at the very bottom for the appropriate p-value. One thing that's not included here, and I kind of harped on it in the last video, is of course the distribution of the residuals. And that distribution of the residuals really tells us a lot as to whether we actually have a problem or not. This is something that I wish we would get better at in reporting within the social sciences, definitely so within economics. I could harp on that for hours if I really wanted to, because this is really where it tells us whether we have good fit or not, whether we're really making a relatively strong argument or we're really kind of making a more of a weaker argument here. So we'll take this information, and now we're going to move on into some more diagnostics of our linear regression model. So I'm going to include another R chunk here, and then I'm going to just hit the plot function. And this is something that's frequently overlooked. It actually went years within R programming and understanding R before I realized that you could plot diagnostics for linear regression models, and I didn't even know. So we'll put first model, just our actual regression model object, and then we need to give it an additional argument here. We need to put the argument which, and we need to say, all right, we need to identify a number. And so in this case, I usually only care for my own particular cases, plots 1, 2, and 4. There are a total of 6 of these plots that it will produce, but those 3 tend to be the ones that I care the most about. So we will, is that going to run? Okay, we got an issue here. What's going on? I don't understand. We're stuck. Okay. Do I have something's stuck there, and I'm not quite sure what is stuck, but something is. Alright, we're stuck. We've printed. Okay. There we go. There we go. Yeah. Okay, fine. I'm not exactly sure what happened there. Alright. See, this is the example of if you don't put results as is, it'll actually produce all of this HTML code, and we don't actually want that, so I'm just X out of that, so that doesn't show up for us. Great. So sorry about that. So the first plot that it produces is a kind of a two-way plot. We'll take the fitted values of our regression model, which basically this is our econometric model imposing that the error term is 0. So we could say if we were to find what would this model predict for all of our observations, given everything that we've observed with our independent variables, all of our x variables, and the estimated coefficients that we have, whether they're statistically significant or not. What are the fitted values? What are the predicted values for y? So we can kind of say, what's our hypothetical dependent variable? And then we actually plot that against residuals. So if we take the residuals and then we take the fitted values, we force those into coordinate pairs, and then we plot them here, and that's exactly what this plot is. Now, theoretically, if you think about this, what should this produce? We should have residuals that are evenly distributed, both positive and negative, relatively close to 0. You'll have along your x-axis, basically, this should pass through the average value of your dependent variable, and so this will have some scale to it. This shouldn't really have much of a scale to it. It should be centered around 0. And we should have a whole very wide open dispersal pattern of all this. There should be no pattern, really. But beyond that, we should have effectively a whole bunch of observations and no real clear trending behavior. You shouldn't be able to look at this plot and see anything systematic at all to it. So the fact that we can look at this plot and see something systematic tells us we have a problem. We have clustering behavior happening here. We have some clustering here, some clustering here, some clustering here, and some clustering here. And this should not be. This should be evenly dispersed. It should be very random, if you will. It shouldn't have anything systematic in it. The fact that we have something systematic here tells us there's something here that we're missing inside of our linear regression model, at least our baseline model here. So this kind of gives you an indicator of, have we modeled things correctly? Has the applied researcher really done due diligence in trying to explain our dependent variable. Great. So I'm going to take this R chunk, line 75 through 77. I'm going to copy it. I'm going to paste it right down here below. And then I'm going to switch this from which equals 1 to which equals 2. And then we will re-execute this line. The second plot that I usually like to look to is the QQ plot. Now, a QQ plot basically is a plot of standardized residuals around the quantiles of our model. Now, in theory, you kind of have this dotted line of where things should behave, and you should see a whole bunch of observations. This usually happens around the middle of the distribution that are right on that line. So the fact that we see a whole bunch of them on this line, that's a good sign. Now we deviate from that line initially or earlier on this, the positive end of this rather than on the negative end of this. But nevertheless, this usually forms kind of like an S or an inverted S curve, depending upon the actual scale of the data. So usually you'll see on one side of this, it'll kind of go up above as you get into the extremes of the data, and then it will go down below on the opposite scale of this. So it kind of forms almost like an S shape. Now, this one in particular is kind of not quite what we would theoretically say is our normal QQ plot. It's skewed a little bit here. We start to deviate considerably from this dotted line here earlier on, right after we hit +1. And then, of course, we don't do so here until we get closer to -2. So we're still kind of skewed, if you will. Additionally, we start to see some pull away here happening towards the end. This is rather normal looking in terms of the overall shape. This not so much. We have a relatively large gap happening down on the lower end of this, and as a result, this is creating some of our skewness, if you will. This is likely to cause some problems. We're basically indicating here in this plot, are our residuals normally distributed? Do they meet that assumption of normality? Now, recall from our previous video where we actually talked about the assumptions of our OLS estimator, we said at the very last, the last of those assumptions was normality. And I mentioned in the slides, not necessarily needed for producing point estimates. And that's true. It's not. We use normality whenever we're talking about confidence levels and whether we're talking about statistical significance. So going back up here, normality is used to produce the t-values and the p-values and for this portion of it. For us to identify, okay, yeah, the coefficient for the rank of associate professor relative to assistant professor, that's statistically significant at this particular level. Now that's an assumption based on normality of our error terms. Once again, reiterating here that it's these residuals that define everything of importance to us. So we see this, and it's not terrible. I've seen worse. Let's put it that way. I've seen much worse, but this still isn't exactly optimal, if you will. This indicates again we probably should do something. So both of these plots are kind of telling us the same thing. We need to do a little bit better from a modeling perspective. Finally, the last one that I like to work with is Cook's distance, and this one is going to be plot number 4. Now, Cook's distance, there's a full calculation behind what Cook's distance is. Again, I'm not going to get into the math of this. This is an applied kind of econometrics online course. It's not necessarily dealing with all of the mathematical terminology. We can certainly do a more theoretically driven one, but we're just not at this point. But Cook's distance, what's far more important is the interpretation. It tells us which of our parameters, which of our observations is likely to skew the parameters. And so the taller these spikes, and these spikes correspond to individual observations, the taller these spikes, the more likely they are to skew our estimation. Now, R does a really good job of identifying each of these individual observations. It usually takes the top 3 and it'll pinpoint the numbers for that. So I'm actually going to go down here into the console, and let me clear that out a little bit, and I'll take the whole salaries data set, and then I can actually put in these individual observations. So let's do 283, and then what's it, 293? Yeah. And then what's the last one? 333. Make that bigger. Great. So we have these 3 observations, 283, 293, and 331, that are likely to be outliers. They're likely to skew the parameter estimates. And if we look at these individuals, we get kind of a different picture as to who they are. So for 283, we see this is the rank of a full professor. 51 years since they received their PhD, so they're more in the twilight of their career. And they've also had 51 years of service. So this individual came out of grad school, took a job at this university, and never left, in all probability, unless they're working into their 90s. This person, they're probably towards the end of their work time, and so they most likely they clearly have been at this university the entire time of their professional career, and of course they're male, gender, and their salary is on the lower end of the spectrum in terms of the average salary. It's well below the average salary. So yeah, we can see why that would skew this observation. Individuals 293 and 331, they tell a slightly different picture. Again, both of them are professors, different disciplines. They're also towards the end of their tenure here, although not nearly as much as 51 years. You've got years since received PhD, 39 and 49 respectively. But we see 2 different things happening here. So you've got one person who has worked at other universities and clearly moved from one university to the next, because they've only been at this current university for 9 years. So they've had some time. Maybe they may have jumped through multiple university changes, in which case they've been able to capitalize on different market movements. And that's one way to kind of move up in terms of salary within the academic community, is stay a few years and then go back on the job market. And if you've maintained your marketability, then you're likely to benefit from a higher pay, although you end up disrupting your life all over again. It's hard to set down roots. It's hard to not lose money in terms of if you buy a house when you move, etc. But you are kind of compensated for that. And clearly this individual has kind of done something similar, because they have a salary range that's exceptionally high with respect to the average. And then the second person, observation 331, they clearly worked at this university before going into academic teaching. So they have years of service 60, and years since PhD 49. So they worked for some time within this university before. Then they decided to go get their PhD. They got their PhD, and then they started working in and working their way up from assistant, associate, to full professor. They are also on the higher end of the salary range. This tells me that this person probably is in administration somewhere, but they still maintain their faculty status, but they're probably doing something within administration, just based on my own individual knowledge. It's possible they're not, but I just have a feeling. All right, so great. So this helps us identify some of what we're dealing with. So maybe some of this has to do with rank. I mean, clearly we have a rank thing here happening, because all of these are full professors. Definitely there's some years since PhD attainment that's happening. It may be discipline related. It may not be discipline related. It's kind of hard to say on that. So at this point, we probably should look at what we would refer to as interaction terms. And that may be the next step to go in terms of making this model better, if we possibly can. So let's do just that. So we'll create a new section. Yeah, interactions of, and then let's just to start with one, gender and rank. So this data set was initially put together with gender in mind to kind of examine gender pay inequality that's happening within academia. So that immediately I'm kind of geared towards, okay, let's try to find this gender interaction, because in our initial estimations, gender was not necessarily important by itself. So let's kind of see if we can dig into that. The first thing we're going to have to do with that is we're going to have to create a separate variable for the log of salary. And there's a reason being for it, but I'm just going to take my salaries data set and I'm going to append it. I'm going to create another column by subsetting, and I'm going to call this log salary. And then we'll actually say, okay, now I want the natural log of salaries, but I want this to be the salary column within this data frame. Next, we're going to kind of summarize this data a little bit, and we're going to use a function called summary SE, and this is located within that RMISC or R miscellaneous package that we downloaded before. And here we need to specify, all right, I want my salaries data, the measure variable that I'm interested in this case, it'll be equal to log salary. This has to be a column name that you feed this this function. And then the group variables that I'm interested in grouping by, there will be the combination of sex and rank. Excellent. And then let me just print this down below so we can take a look at it. All right. I guess we don't need to make that any smaller, but I probably should make that smaller. There we go. All right, so what this does is it basically estimates kind of taking a difference in means test, if you will, but it'll calculate both confidence intervals for the measurement variable that we're after, in this case the log of salary, based on both the sex and the rank factor variables. So you can see we have the two options that we have available here among our binary gender. We have female, and then we have all three ranks, and then we have male, and we have all three ranks. We can actually see the disparity happening here within the number of observations within this, because we're capturing the full range of these groups, both by binary gender as well as by rank. This would sum to our full data set, 397 observations. We can see the actual average value for log salary happening within each of these groups. And then we have we have both the standard deviation for all the groups, we have the estimated standard error for them, and then we have a confidence interval that's happening there. So this kind of gives us everything that we might possibly need in order to kind of show this visually. And that's really the purpose for me to generate this table here, is I want to be able to show this graphically, the interaction between rank of our professors as well as our binary gender. So I'm going to add another R chunk, and then we're going to generate a plot. So this is going to be a ggplot graph that we're after. We're going to feed this the some data frame that we've put together. We'll define our aesthetics. For X, we want this to be rank. For Y, we want this to be log salary. And for color, we will use the factor variable of our gender. Great. Now we will add to this geom error bar, and we'll define the aesthetics of that. We need to specify both the minimum and the maximum for this on the y-axis, so we'll specify ymin equal to log salary minus SE, and then Y max, we're going to set that equal to log salary plus SE. We need to specify the width. We'll specify the size. And then we'll specify position. And in the position of this, we need, if we don't specify a position, dodge, which is basically the kind of the separation so that we can overlay one over the other. They will be directly on top of one another. So we're kind of need to break these apart and kind of put them side by side. So we'll dodge them by 0.3. We will also put here a GM point. Let's specify shape equal 15. The size of this we'll set equal to 3. And again, the position equal to position dodge of 0.3. And then the final last thing we'll do is put some labels to make it look pretty. So we'll set the X label equal to rank. And the Y label we will specify as log of salary. Fantastic. And this generates the following kind of almost box and whisker plot. It's interpreted like a box and whisker plot, if you will, but basically this gives the confidence intervals and the difference in means of these along these two dimensions, both the rank of both assistant, associate, and full professor, broken apart by our gender categories. So we can see here the female gender is lower. The mean value is lower, and in all three cases, for all three rank types, the average value is lower than that of their male counterpart. But what I find exceptionally fascinating is that it's wider too. There's less of a dispersion among the salaries at every rank level for the males than there is for the females. So there's something happening here where the females are being treated differently in terms of outcomes. There's different things affecting their actual outcomes, and this could be anything from a hypothetical penalty for family planning, or real actual penalty for family planning. Whether it's perceived within hiring practices, or whether it's actually explicitly there. So that is one way of possibly explaining this. I do find it fascinating that they move up almost in scale. The difference between associate professor, it grows greater than what is there for assistant professor, but then it kind of shrinks and collapses with full professor. So there's still upward mobility happening, and it's happening proportionately, but it's still not quite equal in that regard. And I'm curious if this happens in other industries as well, because it could be that the dispersal pattern is what's oftentimes picked up when we talk about gender pay inequality. Now, I don't deal in this literature at all, so I'm sure there's far more qualified people that can discuss gender pay gap with a bit more eloquent language. But looking at this from a data perspective really kind of tells an interesting story, and one that hopefully we can try to pick up now with our linear regression model. All right, so about this point where our video is getting long enough, so I'm going to cut it off here, and we'll pick back up next time where we'll try to account for some of these interaction terms within our next our next second try of our linear regression model. Thank you guys very much for watching, and I'll talk to you next time.